So I would like to thank the students who will make me some question after, telling me that some part of that the end of my course last time was a little bit too fast. And they are completely true, and I hope they will continue to make questions, either after the course or during the course. So let me come back to the decomposition of invariant measure in ergodic measure as a connected sum of ergodic measures. So I'm always with some compact manifold on F. I take diffeomorphisms, but homeomorphisms could be the same. But so yesterday I introduced a set of probability on M. I say that this one was a compact convex set, metric set. On inside, I have the invariant measure, invariant probability measure for F. And I think I forgot to say that these invariant measures are also compact on convex, because if you make some combination of invariant measure, it remains invariant. Okay. Now, if you have, I don't know, some measures, nu1, nu k, in so invariant measures, and take coefficient alpha 1, alpha k in 0, 1, such that the sum of the alpha I is 1. So the fact that it is convex says that the alpha I, nu I, so mu, is also belongs to the set of invariant probabilities. So now let's rewrite that in a more complicated way, just for fun. So as I have the alpha 1, alpha k with the sum is 1, if I look at this compact convex metric space, I can look at the Dirac measure at that point. Nu I. So that is a probability of the set of invariant probabilities, which is a metric space, so I can take probability on it. So I can now look at the sum of the alpha I, the Dirac measure on that space. That is a probability on my compact metric space PF. Okay, so let's call this probability theta. And then, if I want to define my measure here, I just, this measure, mu, is defined by for any continuous map from M to R, I will define the integral of phi for mu as the integral for theta along all the probability on P and F of the integral of nu of phi de mu. Well, okay, it's just for making more complicated was something which was very easy to understand. So that was easy to understand. That is very difficult to understand, but it's the same. Okay? Just taking this probability here. Because if you look at this integral, you have, in fact, to make the sum of the value along this one, and you remain to the sum of the integral of alpha e times this one. Okay. And so the convexity says that taking this probability, making this complicated formula, it's remain inside, it's defined a new probability which is still invariant. In fact, what I have done here for a probability which is supported in finitely many points, measures, but you can do that for any probability. For any theta probability on my metric space P of F, I can define the same formula, so I will not rewrite that. So now if you look at that, defines a probability on M. A probability which belongs to the invariant probability by F. So that is making a convex sum of probabilities following these coefficients. These coefficients which are substituting my finitely many coefficients here, alpha I. Okay. So the theorem of yesterday, so about the decomposition in ergodic measure of any measure was that, so the theorem was for any invariant probability mu of P of F, there exists a unique probability on the invariant measure by the invariant probability by F, such that the weight of the ergodic measure, so there exists X in P of F with theta of X is 1 on X, in fact is included in ergodic measures. Well, in P of F with for any nu in X, nu is ergodic. Okay? So my probability give a weight 1 to the ergodic probabilities, and mu is given by that formula. Is given by the integral of phi d mu is the integral for all probabilities, invariant probabilities, to so that is really telling that my probability is a convex sum of ergodic measures. So sorry, yesterday I have been very fast in giving this formula without explaining what was the meaning. Okay. Let me go to the end of my talk of yesterday, that it is Birkhoff theorem, and let me explain Birkhoff theorem in another way. So I can keep my favorite dynamical system. And now, giving a point x in M, I will say that x is positively regular if you look at the average of the Dirac measure at the iterates of x, these converge to some measures. So limit exists. And in that case, I will denote it mu plus x. So that is a point which is positively regular. This means that, so in an equivalent way, this means that if you take any continuous function from M to R, then the sum 1 over n sum of the value, so the average of the value of phi at the point of the orbit of x tends to something. The limit exists. Okay. So that is a point which is positively regular. That is, if you have some function, you can make statistic on the function along that orbit, along the positive orbit. So in the same way, you can define negatively regular which is the same replacing the positive iterates to the negative iterate. That is limit of the sum 1 over n, the sum of the n minus 1, so the Dirac measure at f minus I of x exists. In that case, I will denote it by mu minus of x. So I have points for which I have good average of function along the positive orbit, other points for which I have good average along the negative orbit, and I will say that a point is regular so x is regular if it is positively regular and negatively regular and if the two limits are the same. Okay. And so now I can restate Birkhoff's theorem. If you look at the set, so you have F, diffeomorphism or homomorphism. In fact, I don't need a manifold. It can be on any compact metric space. If you look at the set of regular points, and if you look at any invariant measure, for any invariant measure, the weight of the regular point is 1. So that says that the almost every point for mu has good average for the positive orbit and good average for the negative orbit, and they coincide. Okay. The second thing is that if mu is ergodic, then for the set for almost, so there exists, I will put R mu, the set of regular points, so there exists R mu included in the set of the point of regular points with mu of R mu is 1. So that means almost every point for mu, and mu plus of x is equal to mu minus x is equal to mu. So this is telling that for almost every point for mu, the positive and negative average are given by the integral of mu. That's the equivalent statement as I told you yesterday. Okay. So let me come back to the examples of dynamical system that I showed you yesterday for starting, because I will now pretend that this theorem is telling you the answer of the question, where are going the points? Where are going the orbits? And so let's come back to the simplest dynamical system, that is, so examples, 1 or 0. F is the time 1 of a gradient of a Morse function. Okay, so I recall you the picture I have made yesterday for that. So you have some Morse function psi on R. And so all the orbits are going to attracting points and comes from repelling points. And just some specific orbits are going to the saddle. And so there are the invariant manifold, the stable manifold of the saddle, which bounds the basins, which divide the manifold in the basins of the attracting points. The same for the unstable manifolds of the saddles, which are so that are the stable. So the unstable manifold are dividing the manifold in the basin of the repelling points. Well, is there someone in the students who know what are the positively regular points? Is there many positively regular points for such? Alguien sabe? ¿Alguien se anima? Yes, all points are positively regular. Why is that? You take any point, for example, this one. The orbit is going to that fixed point. So if you look at, after a long time, its orbit remains here. So if you look at this sum, forget the first one, because you are dividing by n, so if you forget the first points, it's not important. You take n very huge, so the first from 0 to some n0, it's divided by n, so it's a weight almost 0. So you just look at the last one. And the last one are all very close to this one. So you are just, if you take a continuous function and you make the evaluation at that point, just by the continuity, you have that the value is almost the value of this point. So you get only that. This orbit just see this measure just see the limit point. So if you take some point x in the basin, if x belongs to the basin of this attracting point A, and then mu plus of x exists and is the Dirac measure at A1. If you are in the stable manifold of the saddle, the same. Just you will change the Dirac to this one, to the Dirac to the saddle. So you get that every point x is positively regular. Negatively regular too. So, and what are the regular points?
Critical points.
Only the critical points are regular, because any other point, if you have a point, if x is not a critical point, is not a fixed point, if x does not belong to the fixed point of f, then the limit of f minus I of x is some periodic point, but is distinct from the limit of f of the positive orbit. So we get that mu plus of x is not equal to mu minus of x. My point is not regular. So it's also easy to see that the ergodic measures here are just the Dirac at the fixed points. On the set of invariant measures are just now the bicenters between these, the convex combination of the Dirac measure at the critical points. Okay, so now you see, if you want to know where is going the orbit, I have to understand mu plus of x. Where is going x? The answer is, if x is regular, then it's mu plus of x. That is the place where is going x. So the answer to where is going a point or an orbit, it's a probability. Okay, so let me go to the other example we have seen. So for that, I have a little bit to adapt Birkhoff, because I'm just looking a non-invertible map. So you look at the multiplication by 10. So example 2. Okay. I will not make the same questions because it will take more time for answering. So I will just start for telling that there exists x, which is not positively regular. How you do that? You take a point, so a point is a number of the circle on S1. So a point x is equal to 0, x1, xn, and so on, with the xi belongs to 0, 9. Okay? And now you take a point like that you will start with many 0. But after you put many, but many, many, many 1. So when you start to think, oh yes, if I make average, all the weight in the interval between 0 and 1/10. So on the cycle, so when you iterate, I will look at the weight of the intervals. I guess I will make, okay. So, well, don't ask me to make it. It's okay. And so on. So I start with many zeros. So for a long time, I think that the orbit of X is giving, if you look at the average, so when I look at the iterate, I'm just switching the comma. So the first is 0, so I know my point is there. The second is 0, I know that the image of my point is there. The third is 0, I know that the second iterate of my point is there, and so on. So if I look at the sum of the Dirac along the first orbit, I just see something whose support is in that interval. So all the weight is in that interval. But after, I start to make some 1. So when I arrive to making as 1 as high at 0, I get that the weight of this interval is the same as the weight of this one, on 0 for the rest. Okay. But I continue much and much and much and much, so that at some moment, this one is not 1, but almost 1. So it remains very few things for this one, and 0 for the others. Then I put 2 during more and more and more and more and more and more. And so, if I make this average during a larger time, I have the impression that my orbit just spent all this time in the next interval. Okay, when I see that it's almost like that, I stop and I put 4. But for a dimensional number of times, so that I will think that sum of the delta, the fi of x from 0 to n minus 1, 1 over n. Okay, this, if I look at the weight it's giving to this interval, well, it does not converge, it oscillates. That is, at each moment, you have the impression it gives all the weight to some interval, then to 2 intervals, then the first disappears and you get all the weight to the next one, and you continue like that. So there is no limit. This point is not positively regular. So in fact, there are plenty of points which are not positively regular. It's not difficult to invent any stupid behavior as you want. But Birkhoff says that the measure of the positively regular point, so Lebesgue measure, because Lebesgue, we have seen that Lebesgue is invariant and ergodic. Lebesgue is invariant and ergodic. So Lebesgue of the positively regular point is 1. And furthermore, if you take almost every point, almost every number for Lebesgue, if you look at the weight it will give to each of these intervals, it will be 1 over 10. So if you take a point at random for Lebesgue, of all the digits appearing, which appear in its decomposition. Okay. So the answer to where are going the orbits for the multiplication by 10, well, you want to say that not for just for one point, because you have so many behaviors that you have to decide what is satisfactory for you. Is for you many points means almost every point for Lebesgue, then the answer is the orbit go to Lebesgue. The equilibrium is no more a point, or the equilibrium point is a probability measure, it's Lebesgue measure. almost every orbit, its average tends to Lebesgue measure. Okay, what I want more? Okay. However, once more. There is one more example. In my list of examples, there was two examples. But one was the Anosov. So if you look at A from T2 given by, so A in SL2Z, and if you prefer A equal to 2, 1, 1, 1. So I asked to be Anosov, meaning that the eigenvalues, there is some so two real eigenvalues with the modulus different from 1. Okay. So the determinant is 1, so Lebesgue measure is invariant. And I will show you now that Lebesgue is ergodic. That is the simplest case of a famous argument known as Hopf argument, because Hopf used it for the geodesic flow of hyperbolic surfaces, compact hyperbolic surfaces, but it's easier to do for these Anosov automorphisms. Okay. What is the proof of that? We know that the set of regular points has total Lebesgue measure. So if you look at the set of regular points, let's put reg of F. So I know that Lebesgue of the regular points is 1. So, however, if you look at the torus, so the torus I will represent here as a square, so it arrives with two foliation by parallel lines to the stable and unstable directions of the matrix. Okay? As I have some so I will inclinate me like that, and I will make Fubini like that. So I have a set whose measure is 1, and this set, I can take that it is the integral along that direction of the intersection of that set, the integral on that direction of the intersection of that set on these segments. You want that it is 1, you need that there is at least one segment for which you have full measure. So there exists one unstable segment. So there exists one segment, EU, tangent, included in an unstable leaf. Unstable leaf means the foliations by lines parallel to the eigendirection corresponding to the exponent larger than 1. So to the eigendirection of lambda larger than 1. So you take the eigenvalue of that, one is larger than 1. You take all the lines which are parallels to these direction, to the corresponding directions, that is unstable foliation, and so I have unstable leaves. So there exists some segment in an unstable leaf, such that if I look at EU intersection with the set of regular points for f. So if you look at I will look at Lebesgue associated to EU. So that will be equal to 1. Or if you prefer, maybe it's easier to understand with the complementar with the points which are not regular, so we'll put a C here, is 0. I have a segment in which there is almost no point which is not regular. Okay? So let's assume that it is that segment. In that segment, almost every point is regular. So now take 2 points in that segment. If you have x, y, which belong to yu. I will look at the negative iterate of them. Look at f minus n of x, f minus n of y. And I want to know what is the distance, what is the length of the segment, of the unstable segment of that. So that is an eigendirection of my matrix. So it's invariant. The direction is invariant. So 2 points being a same unstable segment, their iterates positively or negatively remains in the same unstable leaf. Maybe not this one, but in another one. But now there was in a direction which was expanded by a factor which was lambda larger than 1. So if you look at the distance between, so if you look at this distance is 1 over lambda power n, the distance of x, y. Because the vector tangent, so you have x here and y there. And if you look at this vector is each time multiplied by lambda minus 1 when you iterate negatively. So this makes this segment decrease exponentially. So now, as the 2 points are approximate the 2 orbits are approximating one to the others, if you make the evaluation on some continuous map, as a continuity is absolute continuity because of compactness, you get the same result. So if one point was not negatively regular, the other not too, and they will oscillate together. The average along one of the points with the other, if you look at this sum for x and for y, the difference tends to 0 for all the large number. So forget the first one because there are no interests, you divide by n. And so the average will be the same. Okay. But there is at least one regular point. So we know that there exists, if you take x regular, so you have mu minus of x, which is equal to mu plus of x, but and you have so that for any y in this segment, mu minus of y is defined and is equal to mu minus of x. Okay. So now if you just take the regular points, you will know that mu minus of, so if y was regular, you get that mu minus of y is equal to mu plus of y is equal to mu minus of x is equal to mu plus of x. Okay, so we know that all these segments here have the same negative average. Now, through these regular points, just look at the regular points and take the stable segment through the regular points. You just take the stable segment through the regular points. And now you iterate positively. Well, if you have one point here, positively, you are multiplied this time by lambda minus 1, because eigenvalue has lambda minus 1. So the distance tends to 0 by positive iterate. So they have the same positive average. Okay, so now you know that for any segment through y in the regular points of f intersected with my unstable segment for any segment z belong to a segment through I have that the positive iterates of z has a well-defined limit, and it's equal to mu plus of y, which is equal to mu minus of y. Okay. And that is also equal to mu minus of x. That is, it does not depend of the point y. So let's call that mu of x. Mu. Let's call that mu. I fix some x, fix x. Fix x, so I call this limit mu. So I will put is equal to mu. So how many points has positive iterates tending to mu? Well, all the points through the stable manifolds of the regular points in this segment. But if you take these segments, they cover the whole torus. Not the whole torus, because here it's not all the points, but it's almost all the points. So now if you make once more Fubini, if you take segment of sufficient large size, the area in the torus of the union of the segment through these regular points will give the total area in the torus. So the conclusion is, for almost every x in T2, you have that, maybe not x, z in T2, you have that mu plus of z is defined on is equal to mu. Okay. Now we can make exactly the same argument reversing taking one of these stable segments and taking the unstable one. You get also that for almost every z in T2, mu minus will be mu. You take the intersection of this, it remains a set of full Lebesgue measure of area equal to 1. And we get that almost every point has a well-defined positive or negative limit, and this limit is the same for everybody. Well, it remains to, I did not recall here that the averages of the averages give once more the initial measure. That was in the statement that I gave you yesterday, and that implies that mu is equal to Lebesgue measure. So you get that almost every point is following Lebesgue measure. So we get like that the ergodicity of Lebesgue measure, telling that even if for the Anosov map you have plenty of behavior, almost every point is attracted by Lebesgue measure. The equilibrium will be Lebesgue measure. Okay. So that's very nice. Birkhoff tells us that if you have an ergodic measure, you know where are going almost every point for this ergodic measure. But as we have seen in the simplest case of the gradient of the time one of the gradient, the gradient of some Morse function, If you look at an ergodic measure, it's maybe very few points. In that case, it was finitely many points. So Birkhoff, a priori, tell you something just on that point, nothing outside. And certainly, if you want to be happy in your description of your dynamics, you don't want just to describe, Birkhoff applied to the gradient of a Morse function, tell you, if you take the fixed point, the average is the fixed point. It don't tell nothing else. So it do not give you any information on the points outside the support of the invariant measures. So it's not satisfactory. For example, I will not be able with just Birkhoff theorem to tell you where are going the orbits for the last example I gave you the other day, yesterday, that is for the solenoid, where I had a solid torus which was sent inside itself twice. So for that, we will need a new definition. So two definitions. Given a measure mu, so if you have mu, an invariant probability, we will call the basin of mu is the set of positively regular points such that mu plus of x is equal to mu. And we will say, so that is the first point, and we will say that a measure is, so that there is different terminology because it's not a so old concept. So we use SRB measure. That is for Sinai, Ruel, and Bowen. Not for the definition, but for the fact that they prove the existence of such measure in particular in the case in the example I'm giving you. Some people prefer physical measures. If the basin of mu is large in the sense that we think to be a usual sense of a large set, that is, the Lebesgue measure of this basin is strictly positive. So we will see that a measure is an SRB measure if it has a basin with positive Lebesgue measure. So, for example, for the so that is a notion of attracting measure. That is, if you have an attracting measure, you think that it will attract many points. So, for the example, for the gradient of the Morse functions, the SRB measures are the measure based on the Dirac measure on the attracting points. All the other, there was just the stable manifold going to them, so there was no positive Lebesgue measure. Okay? And so, with that notion, I can now go to the last example I gave the other day. So I have f from M to M, from S3 to S3, which admit a solid torus. You have here D2 time, S1 times D2, where you had that on S1 times D2 was on the form TZ go to, I think I put 2T, and I did not remember Z over 10, plus power 2p t e t over 2. Okay, that was the formula I gave you the other day. So let's take f like that. And if you look at, so remember the pictures, that in that sense, the solid torus inside itself turning twice and diffeomorphically. Okay. So here there is a specific measure. I really would like to go to foliation now. So if you take any segment which is transverse to the disks, and you induce, you look at the restricted Lebesgue measure on that segment, the length measure, if you want. And now you make average of the iterate of that segment. First, what's happened to that segment? When you iterate, as you multiply by 2, the lengths become larger and larger. And in that direction you are contracting, on this one you are expanding, so it remains some segment starting to run like that. Okay? And if you look at the probability measure, which was the length probability on that segment, when you iterate, you just obtain the probability consisting of, you take the length on the iterates. So when you iterate n time, you get 2 power n for the length. You take these not probabilities, this measure, and you divide by 1 over 2 power n for getting a probability. Now you make the average of all this probability. Okay? And so you will get a probability. Now, how can you understand that probability? That probability, let's try to look it inside here. So you have a segment which will pass many, many times, but each time it passes, so it cuts like that. On each of these segments, what you see is the length multiplied by some factor. And you make the average of that. So at each time, if you restrict it to that cylinder, what you have is the length of some segments multiplied by a transverse probability. You put some weight on each of these segments, which is the weight of each segment. So you take the length measure multiplied by its weight. And that is the measure at each step. So the limit is like that. The limit is, you will have here, if you iterate this picture, so the second time you have something going twice and then and so on. So at the limit you have a one-dimensional lamination. And the limit measure here will be a measure which looks locally that like a product of the length measure by a transverse probability. Okay. This measure makes that, so as this measure induce Lebesgue on each, so we have to prove that this measure is ergodic. So we prove that this measure is ergodic. So we will have that if you take any, almost any of these segments, almost every point on that segment is regular. And now you look at the same argument that I have done for the Anosov map here. You take the regular, which are the regular point on some segment, which are almost every point, and you look at what are the stable manifold of that point. But if you take a disk through one of these points, what's happened is that it's multiplied by 1 over 10 each time. So all points, 2 points in the same disk will have the same future. So you will get that every point on a disk in a regular point is positively regular, and we'll have as an average the measure you have on your attracting set. And that is, so the union of all that disk will have full Lebesgue measure in the solid torus, and that is the attractor in the sense of the measure for this situation. So that is what will be the SRB measure in that situation. So I know that I'm not explaining with sufficient details, but it's not an easy concept, and you have to make an effort for that. Yeah, there is something to pay, so, okay. Okay. That's all I wanted to say for the general ergodic theory. But I think that starting with foliation at that time, it's a little bit crazy. So I will not start on foliation now. So I stop here for now, no?
Any questions? What are the ergodic measures for the, for example, for the Indenoso? Indenoso,
Yes.
torus 2111. Which are the ergodic measures? Are they really forms or CT?
¿Quieres saber cuáles son las otras medidas ergódicas? Hay muchísimas.
No sé, pero son concentradas en órbitas periódicas.
No.
¿En total o otras?
Hay muchas otras. Hay, bueno, voy a contestar para disculpa el resto de los públicos que no saben, pero hay muchísimos herraduras de caballo incluidas dentro, y cada una de ellas contiene infinidad de medidas. En la verdad, aquí las medidas genéricas, tú tienes un convexo de medidas, y tú puedes mirar, tú tienes la topología, entonces tienes una buena noción de G delta densa dentro de este. Entonces, las medidas genéricas son ergódicas y tienen soporte total. Entonces, genéricamente, tú tienes infinidad de medidas con el mismo soporte, pero que el soporte es Lebesgue, pero no.
O sea, hay muchos campos invariantes.
Sí, sí. Sí, pero es peor que esto, sí. ¿Otra pregunta o other question?
En el segundo ejemplo, de multiplicar por 10 en S1, has dicho que la medida de Lebesgue del conjunto de los positivamente, de los regulares positivos es 1. Entonces, para los irracionales sí que existe el límite, no entiendo cómo puede existir ese límite para un irracional.
El límite para los puntos positivamente regulares es que para casi todos ellos su órbita es densa en el círculo y el promedio va a ser Lebesgue. Entonces no son periódicos. Tú estás me diciendo, sí, si era racional y hay que ser periódico, está bien, pero en este caso el límite sería un Dirac sobre el límite, que sería la órbita periódica. Entonces no sería Lebesgue. Entonces, es decir, de ir a una órbita periódica pasa muy raramente. Y en la situación general es que si tú lo quieres topológicamente, vayamos a decir, no hay ningún límite. No hay. Por eso mismo pasamos por la probabilidad. Si se podía contestar a dónde se van las órbitas de una manera topológica, que sea un poco más útil de decir las órbitas son densas, estaríamos satisfechos con la respuesta topológica. Yo no soy muy bueno en teoría de la probabilidad y nunca he aprendido las probabilidades si la respuesta era suficiente. Hizo el esfuerzo de pasar por la teoría ergódica porque ciertamente la respuesta topológica no es suficiente. No te describe el comportamiento de las órbitas. ¿Sí? Entonces, ciertamente, casi todos son irracionales. Muy bien. Eso hace que si multiplica por 10, nunca te vas a ver algo periódico. Por eso mismo introducimos otro concepto, que si hacemos el promedio de su Dirac, ese sí converge a algo, y sabemos qué. para casi todos es Lebesgue. ¿Sí?
¿Más preguntas?
No entendí bien cuál es su conclusión en el último ejemplo.
Bueno, normal que no entendís porque fui a una velocidad terrible.
¿Cuál es la afirmación?
La afirmación es que hay una única medida soportada en el atractor, en el conjunto, si tomas en el solenoide, hay una única medida de probabilidad que tiene muchas propiedades, pero si la desintegra a lo largo de las hojas, lo que ves es la medida de la longitud, es el dt, ¿sí? Y esta medida atracta su cuenca de atracción, tiene Lebesgue total en la cuenca topológica. Entonces, si tú tienes el toro sólido, todos los puntos van hasta este solenoide, pero tienes puntos que van hasta puntos periódicos, puntos que se van hasta puntos no regulares, pero la mayoría de los puntos, si hace el promedio del Dirac a lo largo de su órbita positiva, se van hasta esta medida, que es la longitud a lo largo de las hojas, ves una probabilidad transversal.
Entonces quiere decir que es una medida SRB.
Es una SRB y su cuenca es toda.
Es toda la esfera, de hecho. Cuando por eso son-
Bueno, si la completas solo con un punto, entonces será toda la esfera, sí.
O con un solenoide al infinito.
O si sí,
Igual.
sí.